My solution for bonus problem 2. So we have two masses sitting on a slope connected via some sort of string with a pulley at the top. So they move at the same time. They move at the same time at the same acceleration. And the force of tension is going to be the same between them. So we know that the force pulling mass 1 down the slope is going to be equal to m1 g sine of alpha. So that's just using some basic trig, sine of opposite over adjacent. We know that this is true, and similarly, we know that the force pulling mass 2 down the slope is going to be m2 g sine of beta. So because the masses are connected via a string, we know that the force of tension on this rope here, force of tension 1 and force of tension 2, are going to be equal. And we also know that the rate at which mass 1 accelerates is going to be the same as the rate at which mass 2 accelerates. So the total forces on mass 1, the net force, is going to be equal to the force of tension, that's the force pulling it up, minus the force pulling it down. So the net force is going to be equal to MA, the force of tension. We're going to find this, and from up here we know that the force pulling it down is equal to m1 g sine of alpha. So we can rearrange this equation, divide each side by m, and we got the acceleration is equal to ft minus m1 g sine of alpha over m1. So similarly on this side, we know that the net force pulling this down is going to be the force pulling it down minus the force of tension pulling it back up again. So again, if you write out the magnitude of these forces, you know that the force pulling it down is equal to m2 g sine of beta. So, and the net force is going to be equal to mass times acceleration. So then if you divide the right side by m and the left side by m, you get A2 equals m2 g sine of beta minus ft all over m2. So now the next part, we knew from before that the acceleration of one is going to be equal to the acceleration of the other. So I've written that rule here. So that means that we can set these two terms, these two expressions, equal to each other, and then begin to simplify them. So the first step, we're going to multiply each side by m1, m2. So that means you're going to get m2 out the front of this part and m1 at the front of this part. So now if you expand these out, multiply m2 by this term and this term, m1 by this term and this time, m2 times the force of tension minus m2 m1 g sine of alpha. This is equal to m1 m2 g sine of beta minus m1 times the force of tension. So now if we bring this term to this side and this term to this side, what we're doing is we're adding m1 f times the force of tension, and we're adding the mass of 1 times the mass of 2 g sine beta. We're going to be left with this. So m2 times the force of tension plus m1 times the force of tension is equal to m1 m2 g sine of alpha plus m1 m2 g sine of beta. So now on the left hand side, we're going to factor out the force of tension, because as we said earlier, the force of tension was equal to each other, so we can factor that out. And we're going to be left with the force of tension times by the mass 1 plus mass 2. On the right hand side, we're going to factor out m1 m2g. That's common to both of these terms. So m1 m2g multiplied by sine of alpha plus sine of beta. And then all we have to do is divide the left hand side by m1 plus m2, divide the right hand side by m1 plus m2, and we're left with this final equation for the force of tension. So the force of tension is equal to m1 m2g multiplied by sine of alpha plus sine of beta all over m1 plus m2. So that's the first part of the problem. We've found an equation for the force of tension in terms of the angle and the masses. Second part of the problem, we're asked to find a condition where the displacement of both masses or the velocity is 0 or constant. So what that means is that acceleration is going to be equal to 0. So for each mass, for mass 1, we've just said that the acceleration is going to be equal to 0. And from our expression over here for acceleration, we can set that equal to 0. So 0 is equal to ft minus m1 g sine of alpha over m1. So then we can rearrange that to find that the force of tension is equal to m1 g sine of alpha. We can do the same for mass 2, set acceleration of 2 to 0, and then use the equation, set 0 to m2 times g sine of beta minus the force of tension all over the mass of 2. So we can multiply this by m2 to cancel this out, and then bring this term around to the front. So the force of tension is equal to the mass of 2 times g sine of beta. So now I've got two equations for the force of tension. But we know that the force of tension of mass 1 is equal to the force of tension of mass 2. That's this rule here. So now we can set these two equations equal to each other. m1 g sine of alpha is equal to m2 g sine of beta. And then we can cancel out the g's minus g from each side, and then we're left with this equation as our final answer. So this is a condition which will make the object not accelerate, where acceleration is 0.